everybody, and welcome back to another video. Today we'll be talking about the electronic component of diodes. Now this is going to be the first episode of which I'm going to explain electronic components, and I decided to start out with diodes and then to go with resistors and then every other electrical component. So today we're going to be talking about diodes, different types of diodes, what they do, how they work, and everything about that. So I'm going to be doing this in PowerPoint presentations because I find that easier. First up, what is a diode? A diode is a two-terminal electric component, and it conducts current in only one direction. So it has low, or ideally zero resistance in one direction, and then high or infinite resistance in the other. Now while we say ideally zero or ideally infinite, because actually they're going to have a little higher or a little lower resistance, so it's not always going to be ideally zero or, infinite. They're always going to be a little lower or a little higher. So a conductor maybe has a resistance of 0.2, 0.3. It just depends. It changes, and it's not always going to be zero or infinite, which is why we say ideally. And then here you can see on these two images that the diode is composed of an anode, cathode, and the positive polarity, the positive of your power source, will go to the anode, and the negative will go to your cathode. I will explain forward and reverse bias later. Now for the internal structure, a diode consists of a semiconductor material, which is typically silicon. There are germanium diodes, but more commonly silicon. Silicon by itself is not of much use. It doesn't really conduct anything, so engineers will dope the silicon using phosphorus and aluminium. And that's going to create p-type and n-type silicon, and that is what we use in diode. P-type silicon has a hole, and n-type has a spare electron, so the n-type is going to give electrons to the p-type. Then we combine the p and n-type silicon, and we form a p-n junction, which is a diode. This is what silicon looks like, and that is the atomic number and everything related to the silicon in the periodic table. This is the internal structure. As you can see, the n-type has free electrons and the p-type has holes. And this, what is in the right side, is called the depletion region, and that is essentially a barrier that blocks electron flow. So we need a high enough voltage to pass this barrier, which is about 0.6 to 0.7 volts. Now, forward and reverse bias. Forward bias is allowing current, the diode is allowing current to pass and it acts like a conductor. Whereas in reverse bias, the diode is not allowing current to pass and then it acts like an insulator. As you can see, this is the p-n junction, the depletion region, and it takes about 0.6 or 0.7 volts to pass the depletion region. That is the depletion region, so between the p-n junction, and like I said, it's a barrier where it blocks electron flow, but the higher voltage you apply, the smaller the depletion region gets and the more electrons can flow. And so if you apply low voltage, even in forward bias, it's not going to conduct. So you need at least 0.6 to 0.7 volts. Next, this is a diode conducting graph. As you can see, we have reverse and forward, and we have this thing called breakdown. Now what breakdown voltage is when in reverse bias the diode suddenly starts conducting again. This typically requires a higher voltage, about, as you can see, 50 volts, but this can also go 200 or hundreds of volts. And that is when the diode suddenly just breaks down and starts conducting in reverse bias. Now as you can see, the graph looks like it has this distinctive shape, and it has forward and reverse bias. So as you can see, it's 0.7 volts for silicon, 0.3 volts for germanium, but 0.7 is what we're going to say because silicon diodes are more common. Now, another type of diode is a Schottky diode, and it's very similar to a regular diode. It looks the same and seemingly behaves the same, but the difference is that Schottky diodes have a lower forward voltage than regular diodes, so it takes less voltage to pass the depletion region. So it's about 0.15 to 0.45 volts, which is a lot less than a regular diode, and that's enough for the forward bias. And they have a faster switching action, so they're using switch mode power supplies. And this is achieved through a metal semiconductor junction rather than a semiconductor junction, but I'm not going to go too in detail into that. And then you can see the symbol. It kind of looks like the letter S, but inverted. Not really, but that's the symbol. And this is the graph for the Schottky diode. You can see there's a forward characteristic and a reverse characteristic, and you can see that the forward characteristic is a little closer to the y-axis rather than the reverse characteristic, so not much change there. Next we have Zener diodes, which look orange. They look more orange than regular diodes, and they're diodes that specialize in current flowing in reverse, which means that they have lower breakdown voltages than regular diodes. So it can range from as low as 2.4 volts to 200 volts and all the way up to 1 kilovolt and possibly even more. But the thing is, they have a lower breakdown voltage because they are designed to also conduct current in reverse. So they will have a reverse bias, but it's very easy to make them start conducting in reverse bias again. And that is the symbol on the right for it, and it kind of looks like the letter Z. Then again, not really, but that's the symbol. This is the graph for a Zener diode. As you can see, the forward bias looks pretty much the exact same, but now the reverse bias, we get a Zener breakdown and avalanche breakdown. Now a Zener breakdown is a typical breakdown voltage that is designed, so 2.4 volts, 5 volts, whatever, and then that is designed to go down and start conducting. But avalanche breakdown is when you further decrease the voltage, and that is when the depletion region is even less and it starts conducting even more. So it's going to conduct even more than the Zener breakdown. So avalanche breakdown is just a rapid, faster current flow, so it starts conducting a lot more. Now next we have these nice currents is light emitting diodes, or LEDs. LEDs are also diodes, and they just produce visible light as a byproduct of electricity passing through them. And if we connect them backwards like a regular diode, they won't conduct and they won't light up. And LEDs have higher forward voltages, about 2.3 to 3.2 volts to 2.5 volts, sorry. And they also need less current, otherwise they will be destroyed. So regular diodes can typically take a lot more current than regular LEDs take much less current than regular diodes. So regular diodes can take much more current than LEDs, where LEDs typically have a maximum of 20 milliamps, maybe 30 milliamps, whereas regular diodes can go up to hundreds of amps. And they are connected in series with a resistor. We'll talk about resistors in the next episode of this. So they're connected in series with a resistor, and that limits the current flowing to the LED so that it doesn't get destroyed. Now you can see on the image is a red LED, but they can be blue, green, yellow, they can be white, they can be any color you want. You've even got RGB LEDs, and I just pick red for this because that's the most common. This is the internals, so it's encased in an epoxy case. It's got a tiny little wire in there, reflector carry, semiconductor diode, which is the exact same thing as a PN junction regular diode, and a flat spot. Now you don't need to know all this. All you really need to know is that the anode, or the positive, is the long leg, and the cathode, or the negative, is the short leg. And the cathode is also marked with the flat spot. That's all you really need to know. You don't need to know all of this. Now, rectifiers. Rectifiers are devices that use diodes, and they convert alternating current into direct current. Now, in this series, I assume that you know everything about voltage, current, alternating current. I'm just assuming that you know all of that, so I won't be specially explaining those in separate videos. I'll just assume that you already know. So they are used to convert alternating current AC into direct current DC. And the most common are the half-wave rectifier, or the single diode rectifier, and the full wave bridge rectifier, or just a full bridge rectifier. This is what it looks like. Typically these are higher current rectifiers, like 6 or 8 amps, and they're put in this little case here that has 4 electrodes. This is a half-wave rectifier, so we have a positive peak and a negative peak of AC current. So the AC voltage in our homes has a positive peak and a negative peak of about 325 volts. So it goes up and down, up and down. The current and voltage changes over time between positive 335 and negative 325. And if we put a diode between them, just a single diode, you'll see that we get a pulsating DC. Now you can see that the negative peak is now nowhere to be seen. So the diode doesn't conduct when the negative peak is active, so we only get the positive output of the AC wave. And these are used typically for lower power applications where it's not that important. But if we combine 4 diodes, we will get this diamond shape. And we get what is called a full wave bridge rectifier. And you can see that now the output voltage is a full wave signal, which means that the negative peak is now converted into positive bumps. And you can see that now we have a positive peak on every cycle. And it's DC because it doesn't, change current between positive and negative. So now we get a full wave signal, which means that it's now only outputting positive peaks. So if you input 12 volts AC, you're gonna get about 15 volt DC maximum if you add filtering capacitors and all that. And it's much more powerful than a single wave rectifier, and it's usually used in power supplies and higher power applications, and it just has generally a lot more power than the half wave rectifier. That is all I have to say about diodes, and in the next video I'll talk about resistors, and in the video after that we'll talk about transistors. I just thought it would be good to start with diodes because they are pretty common, but the most common components are the resistors and transistors, and those will be covered in the next videos. With that, I hope you enjoyed and that you learned something, and I will see you in the next video. Goodbye.